just looking at 6.5, so these are the, have your calculators handy too. I'll show you how to do this on the calculator. But the other four trig functions. So y equals tangent of x. Y equals tangent of x has a vertical asymptote starting, or every pi starting at pi over 2. So I'll show you what I mean by that. The period for tangent is different for sine and cosine. We have a cycle every pi. So that's why we have vertical asymptotes. Every pi units, it will break into a new cycle. And we're starting at pi over 2. The reason for that is tangent is defined to be sine of x over cosine of x. And so you have to think about the unit circle. When I'm up here at pi over 2, I'm at the coordinate 0, 1. That places the 1 on top and the 0 on bottom. So therefore it's undefined at pi over 2. So pi over 2, and then 3 pi over 2, and then 5 pi over 2. So every odd pi over 2 multiple there, we have pi over 2. And then the next one, and going this direction, we'd have negative pi over 2. And then we have a vertical asymptote. So go ahead and draw that in. So negative pi over 2 and at pi over 2, we have vertical asymptotes. Notice that they are pi units apart. And then the next vertical asymptote would be at, let's see if I can, let's do this. I want to make this distance about the same here again. So this would be, the next one would be at 3 pi over 2. And over here we would have, of course, a negative 3 pi over 2. And then in between pi over 2 and 3 pi over 2, we would have a pi here and a negative pi here. So, in the assignment, I'm going to ask you to do 2 cycles of these. 2 cycles rather than 1. 2 cycles of them. So one cycle would look like this. If you have the option of, before I even show the domain and range, but you have the option of plugging in points. So if you were to plug in 0 for x, what's tangent of 0 equal to? So think about, on the unit circle, I'm right here. Here would be the coordinate 1, 0. Remember, tangent is sine over cosine, so we would have 0 over 1. So tangent of 0 would be 0. So at 0, I'm at 0. So it goes right through the axis at the origin. What about at pi over 4 right here, and at negative pi over 4? What does tangent of pi over 4 equal? That's where the 2 coordinates are exactly the same. Right here. They happen to be root 2 over 2, comma root 2 over 2. So what would sine over cosine be at pi over 4? At 1. So right here we'd be at 1. And then what about at negative, down here at negative pi over 4? It would be at negative 1. Yeah. Let's do this in a different color here. So I have a few coordinates here. And then you just kind of have to know the general shape of this. It goes like this. It gets closer and closer and closer to that vertical asymptote, and then closer and closer to this vertical asymptote as well. That's what the tangent curve looks like. The only difference between the tangent curve and the cotangent curve, well, a couple differences, but one is that it is reflected over the y-axis, so it's just flipped like this. Okay. And then also, the period will be the same, but the asymptotes are at a different place. They're at pi, 2 pi, 3 pi, etc. Okay, so I'll show you that one in a little bit. But that's one cycle right there. And I'm going to ask you to do 2 cycles. Once you have one cycle and you have the vertical asymptotes, it's pretty easy to get another cycle. You just kind of estimate it. Halfway in between these, it's going to go through the axis. You just draw a quick little curve there. That's it. So, probably the most difficult part of these, once you kind of know what the tangent looks like, is listing the domain and range. And the reason for that is that there's an infinite number of values that cannot be part of the domain. So we have to think of a way algebraically to write an expression to show that its domain is all real numbers except these values. And so a couple different ways you can do that. One way, of course, is to use algebra here. And use an algebraic expression. But we have the domain is the set of all x such that x does not equal pi over 2. So I'm just stating x cannot equal pi over 2. And then plus n times pi. And then I need to say what kind of number n can be here. But plus n times pi. So it'd be pi over 2. And then what I want to do is take, okay, if n is 1, you'd add another pi to that. And you'd be at 3 pi over 2. If n were 2, you'd add another pi to that, and you'd be at 5 pi over 2. So n could be 1, 2, 3, 4. N could also be negative 1. If I had a negative 1 here, it would be subtracting pi from it, which would land me at negative pi over 2. And then negative 2 would place me over here at negative 3 pi over 2. So we need to also state in there what n can be. So you could just say n, where n is a integer. So just in this case, say n is an integer. Some students, it's just too hard to think of all the algebraic expressions. So I will also accept pattern-based listing of the values that x cannot be. What I mean by that is you would say x, the domain, is the set of all x such that x cannot be equal to, you might put pi over 2 in the middle here, and then you might go, okay, and also 3 pi over 2, and 5 pi over 2, and then do a dot, dot, dot. That means continue the pattern. I would be okay with this. And then going this direction, we would have negative pi over 2, negative 3 pi over 2, and then you would go dot, dot, dot. Are you with me? No? Okay. I'm just showing all the places where I have vertical asymptotes. Oh, okay. And I'm showing you clearly what the pattern is that x cannot be, rather than describing it as an algebraic expression. Okay? Either one is fine. Just clearly describe the domain. Okay, is that clear?
Yes.
I'm fine with either one. It doesn't matter to me. Okay, and then the range, of course, is all real numbers, so because it keeps going forever. Okay. All right. Any questions on the tangent function? Should we graph one example of it first before we go to the next one? Flip over to the back. Flip over to the back. I'm going to ask you to do, not the very back, I'm sorry, the back of that front page. So if you flip over to the back, let me find my tangent graph. I have one here. Should have y equals 2 tangent 1/2 x. So the question is, what is that 1/2 going to do? How is that going to change it from the parent graph? And what is the 2 going to change as well? We have a relationship here. The period for tangent is equal to pi over b. Okay, we'll still call that number in front of the x the b. Okay, so pi over b. And so in this case, we have period equals pi over 1/2, which is equal to pi times 2 over 1, or 2 pi. Let's write it out here. So we have 2 pi. So the period is going to be 2 pi this time. So putting that 1/2 in front of it is going to make the period longer. Okay. So instead of going from 0 to 0 to pi over 2, and then from 0 to the left to negative pi over 2, if I want to center this at the origin, which it is, if I plug in 0 here, right? 1/2 times 0 is 0. Tangent of 0 is still 0. So I might as well center it here. per cycle. It really doesn't matter because we have cycles happening every 2 pi radians, but let's center it there. And I'm only going to want to go in this direction out to, when it was pi radians for a cycle, I went out to pi over 2. So where am I going to go here? Just out to pi. So if I go out, maybe put pi here, and then out over here I'd have negative pi. And then go ahead and draw in the vertical asymptote. So if I were to plug in pi over, let's just double check this. Plug in pi here for x. What's tangent of pi over 2? Draw a picture again. Undefined, okay? So did you see why I have a vertical asymptote at pi? If I plug in pi, tangent is undefined. Same thing on negative pi. So that's the process I go through, at least. Just double checking it, make sure I'm okay. I don't graph tangent a lot. Okay, so we're just checking it, making sure we're okay. And then we saw that it goes through the origin. The shape is generally the same. All that this 2 is going to do is it's going to make it kind of grow a little faster. So, for example, if I plugged in, what would be a good value to plug in here to demonstrate that it's growing a little bit faster? Yeah. Let's put in a pi over 2, halfway in between that and a negative pi over 2. So when I plug in pi over 2 here, it's tangent of pi over 4, and tangent of pi over 4 is 1. And then 1 times 2 is 2. So at pi over 2, I'm all the way up at 2 already, so it looks like this. Yeah, okay.
Why are you using the coordinates for pi over 2 for like 0, 1? Because it's pi that we're plugging in?
I'm plugging in pi over 2 because when I plug in pi over 2, I get pi over 4, which is a whole number. That's part of the reason why. It's also halfway in between here.
Well, like when we were plugging in just pi, we used the coordinates for pi over 2.
Right, because when I plugged in pi here for x, I got pi over 2. Yeah, it's because of the 1/2 there. So when I plug in pi over 2, I get pi over 4, which is another easy one to evaluate for tangent. So. And then negative pi over 2, I'm going to be down at negative 2. So there's one cycle. And then if I wanted to do another cycle, I would have, I've got to make sure I get the same distance here. See how there's 1, 2, 3, 4. The way I scaled it, there's 4 vertical lines in between. So I'd have to count 1, 2, 3, 4. And remember, I'm counting not by pi over 4s, but by pi over 2s here. So that would be pi. This would be 3 pi over 2. This would be 2 pi. And then this would be 5 pi over 2. And this would be 3 pi. So if I were to do another cycle here, I would place this right here, and right here, another one. And there's 2 cycles, which is what I'm going to ask you to do. It kind of helps to think about where the vertical asymptotes are located. And then this helps in writing the domain and range, because I will also ask you to write the domain and range. So my domain here would be a set of all x such that x cannot equal, we just start that way every time. Set of all x such that x cannot equal. And what I do is as I go from the origin to the right, I just label the first vertical asymptote, which is pi, plus. Alright, so I have one at pi, I have another vertical asymptote at 3 pi, and then another one at 5 pi. So there's a couple different ways you could do this. You could have something like what I did on the previous one. It could be plus n pi, and then you could let n be odd integers. You can just say that n is an odd integer. That would be one way to do it. And then we just do that where n is an odd integer. Does that work? So odd integers, so we have Yeah, 1, although, let's see, so it'd be 1 pi, 3 pi, 5 pi, negative 1 pi, negative 3 pi, negative 5 pi. Or if you want, you could list them out like this. It's a set of all x such that x does not equal, I'm just going to place in the middle over here pi, and then the next one in the sequence, you guys remember sequences from last year, that's what we're writing as a sequence. So the next one in the sequence would be 3 pi, and then 5 pi, and then dot, dot, dot. And then over this direction we have negative pi, negative 3 pi. That's all. If that's easier for you, I'm fine with that. Just make it clear to me that you know where the vertical asymptotes are located. And then the range, negative infinity to infinity. Any questions on that? You know this is new, so. All right? Okay. All right. So that one, once you get that one, now let's go back to, let's do cotangent next, because they're closely related. I kind of just gave you all the information. I think it's all printed there for you, okay? So just looking at cotangent there on the bottom, what you see real faintly here is not cotangent, but it's tangent. It's like I remember, this is at least how I handle it. I remember in my mind tangent, what tangent looks like. Actually, here's what just like the unit circle. I really just know sine and cosine, and then for graphing, I've added tangent to my memory banks in terms of what it looks like. And then the other three, cotangent, cosecant, and secant, are all graphed based on those three graphs. So it's like, that's why I have this kind of faint shadow here of tangent graph, because cotangent is just this thing reflected over the vertical axis, the y-axis, okay? That's it. And then the other thing is you will notice that the asymptotes for cotangent are where tangent equals 0. Here's why. Cotangent is the same as 1 over tangent. So if tangent is 0, like here, here, and here, can you see the faint little tangent graphs on yours? Or they're not even that faint on yours.
Oh, I drew.
Oh, okay. You try to see. I was looking at it and go, man, that's different. But so don't trace these. These are the tangent graphs. Okay. Yeah. Okay. Well, they're supposed to be faint because they're the tangent graphs. Where tangent is 0, cotangent is undefined. You see that? So where tangent is 0, we have our vertical asymptotes. Once again, the period is pi radians. The range is negative pi to pi. But the domain is not the set of all x such that x does not equal pi over 2 plus n pi. It's 0 plus n pi, because I have a vertical asymptote at 0. I have another one at pi, and then another one at 2 pi. Are you with me? And over here at negative pi. So all that I do is I use this faint graph of my tangent, and I go ahead and just flip it around. But where's the center going to be here? Where is it going to cross through the x-axis on cotangent? Let's draw these in. Yep, pi over 2 and negative pi over 2. So it'll look like this. I'm going to have to use another color. So it looks like that, and then it's going to go the opposite direction. And then it looks like that, and then it goes the opposite direction. So it's a reflection. So those are 2 cycles of cotangent. So once again, the period is the same. It's pi radians. But because cotangent is the reciprocal of tangent, we have our vertical asymptotes at multiples of pi. 0, pi, 2 pi, 3 pi. And then the center is halfway in between at the pi over 2s, negative pi over 2s, and it is reflected. So let's do a cotangent graph. So we can flip it over to the back page. See if we can apply this. So we've got y equals negative 3 cotangent of x. Negative 3 cotangent of x. What's that negative in front of the cotangent going to make it look like? Yeah, so to look like, which graph? Yes. So, but what will be different here is where the vertical asymptotes are located. So the vertical asymptotes here are going to be located at 0 and at, here's pi, and at negative pi. And then here again at 2 pi. So we've got one here. 1, 2, I went too far. All right. So negative 3 cotangent of x, what you can, you always have the option of just plugging in points if you need to. This is where the unit circle comes in. But if I plug in 0 or pi or 2 pi, I'm going to get undefined. Halfway in between 0 and pi would be pi over 2. If I plug in pi over 2, what's cotangent of pi over 2 going to be? Remember, we're at 0, 1. And now cotangent is 0 over 1, yeah. So it's just 0. So we have one here and one here. And then that negative 3, the negative 3 is going to flip it. So now this is going to look like tangent. Okay, so our cotangent would go like this. Let's do a dashed line maybe. That would be our cotangent. And then when we reflect it over, it's going to basically look like this. So it's just like tangent. There's 2 cycles of cotangent. Just keep in mind that any number that comes in front of this x right here, I didn't have to deal with it. It's pi over b. So in this case, we had a period equal to pi over b, which is 1. So period is pi. If you see another number in front of this, it's going to change the period. All right. Any questions on that? Finish graphing it. And we'll look at cosecant and secant. Don't trace these on there. You'll see a faint shadow of sine and cosine graphs. There's a reason for that. Okay. That's the basis for graphing cosecant and secant. Is you draw a little dashed line that represents either sine or cosine. All right. So cosecant. Cosecant, remember, is 1 over sine of x. The asymptotes are at 0 plus n pi, where sine of x equals 0. So in other words, the asymptotes are going to be anywhere where the sine curve, you might want to draw it, this is actually y equals sine of x. So that's the key for graphing cosecant. Here's the first thing you do, is you graph sine of x at a little dashed line. Okay? You graph sine of x. And then all you need to do is find where sine of x equals 0. So find where sine of x equals 0. So right here, and right here, and right here, right here, and right here. So anywhere where it's crossing through the x-axis, sine of x is 0. Those are your asymptotes. The period is still every 2 pi radians. Period is still every 2 pi radians. But what happens here is you have a whole bunch of things that look like a bunch of opposing parabolas, okay? In other words, if you see the peaks and valleys on here, all you have to do is locate dots on those peaks or valleys, and then draw a little parabola-looking thing going in each direction. And how many cycles do I have I drawn here? I don't know, it looks like 4. It's actually not 4 because this one doesn't go with tangent. A cycle is one complete graph where it's not repeating yet. How many of these little opposing parabolas do I need before it starts repeating? 2 of them. So this is actually one cycle. And then from here to here is another cycle. So I've drawn 2 cycles. That's it. And that's all I'm asking you to do. You could plug in points and try to make it a little more accurate on these, but I just did a quick sketch. That's it. Okay, so what's at the basis of this is draw the sine curve. So when I do this example on the next page, we're going to draw the sine curve first, and the sine curve could be moved around from where the parent graph is. And then you draw vertical asymptotes anywhere where the sine curve crosses through the x-axis. And then you draw dots at the peaks and valleys of the sine curve. And then you just draw little parabola-looking things, and you have your curve. So remember, the period is 2 pi again, which should make sense because that's what it was for the other. So here's cosecant of pi x. So keeping in mind that the period is 2 pi, okay, keep in mind that the period is 2 pi. Remember, period is equal to 2 pi over b here. So when I go to find the period, I've got to plug in what for b? Pi, yes. So period in this case is 2. So I've just got rid of the pi's. The period is 2. So I'm in a graph. Y equals basically 2 sine of pi x. Because this is equal to 1 over 2 sine of pi x. Okay, so keeping that in mind, I'm going to graph this. 2 sine of pi x. The period is 2. What's the amplitude? Amplitude is equal to 2, and then it's not reflected at all. There's no negative in front of it. So 2, negative 2. So does sine start low or high? Is sine going to start up at 2 at the origin, or? Yeah, it starts at the origin. And why don't we just scale these by 1s? We might as well. I think that's probably why I set it up this way. So this is 1, 2. We almost have to write it down for these trig functions, though. You can't just assume that it's scaled at 1, because a lot of times it's scaled by rate, multiples of pi, right? So the graph of this thing, let's do a dashed line to graph this. It's going to go, let's get our increment here, is equal to this 2 right here over 4, which is 1/2. So our increment is 1/2. Maybe I should have gone by halves along there, huh? Would have probably been better. Did you guys already label it? Probably did. That's okay. We'll go halfway through. So at half, I'm going to be a pi here. And then at 1, I'm going to be on the axis. At 1.5, I'm down low. And at 2, I'm on the axis. So let's just draw a little dash curve there. Can you keep going? Draw some more. What's that? We need to keep going here. And draw a dash. Oh no, that's okay. So yes, we're graphing. That's why I'm doing dash, because it's not actually. Oops, I went too far there. It's not actually our graph of cosecant. This is just the graph of. I got my dashed line there. So just a little dashed line there. Now everywhere where that dashed line goes through the x-axis, I have a vertical asymptote. More dashed lines. More dashed lines to confuse you. The dashed line. Lots of practice. That'll be great. You have to listen to the recording. I'm recording this, so it'll be really annoying on the recording, yeah.
Why are you recording it?
I record them so that you can keep so that people around here. So I got a little carried away with dash lines. I don't need that many. I want to just do 2 cycles. So I could do 1 cycle here. There's 1 cycle, right? And then right here, another cycle. Okay, so that would be enough. I got carried away with dash lines, but it was fun. So you're drawing the sine curve, and then the sine curve tells you where the asymptotes are and where the takeoff points for each of these are. Okay. What's that? Yep, secant and cosecant are the ones that are going either, little parabolas going up or down, yeah? They both look the same. So this one, if I want to describe the domain would be the set of all x such that x cannot equal, what can x not equal here? Can equal 0, 1, 2, 3, 4, right? So set of all x such that x cannot equal 0 plus just n. You could say just 0 plus n, where n is an integer. And then can you describe the range here? It's not all real numbers, though, because there's stuff in between -2 and 2. It can't be, right? So can it be positive 2? Yes. So it's 2 to infinity union. Okay. I probably should even change the order on those, but negative infinity to 2 and then close. Or not 2, but -2. So it can go from negative infinity up to -2. That's really how I should write it. Usually we write the smaller one on the left, but to it now, well, it's fine. So it goes negative infinity up to -2 union 2 to infinity. So we're just describing the range. I have one more. Yeah, I think I have 2 of each graph is in your homework. That's what this is. So 2 of each graph. Okay, so one more here. Secant graph. What you'll see for the secant graph, because it's equal to 1 over cosine of x, is I have my cosine curve, very faint cosine curve here, and the asymptotes are going to be anywhere where I have a 0. So real easy to do, and of course the little parabolas, opposing parabolas, you're going to take off from the peaks and valleys of those. Now what do you do when you just have a half of one here? Just draw half. Yeah, this is actually 1 cycle right here. From here to here. That's just 1 cycle, and that's okay to do. Okay. You just show half of it. If it cuts it off, that's fine. You don't have to have. So that's it. That's our secant graph. Okay. It's all based. What's that? As the cosecant, yeah, it's the same idea. You draw your shadow of the cosine graph, okay? Where the cosine graph passes through the x-axis, those are your vertical asymptotes. And where the cosine graph has peaks and valleys, that's where your graph takes off from. So you do a bunch of dashed lines, go through that. And so let's go find our secant graph on here. -3 secant, okay. The negative in front, so once again, the period is equal to 2 pi over 1, or 2 pi. So the increment is 2 pi over 4, or pi over 2. That's going to be my increment. The amplitude is equal to 3. So I should probably scale it by pi over 2. That would be a smart thing to do, or maybe pi over 2 pi. 3 pi over 2, 2 pi, and then 5 pi over 2, 3 pi. And then going this direction, it's negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. That might be enough. Negative 5 pi over 2, negative 3 pi. Okay. All right, so remember this is same as 1 over negative cosine of x. So let's graph negative 3 cosine of x. Let's graph negative 3 cosine of x. So cosine typically starts high up at 3. Because it's negative, it's going to start low here. And then it's going to go through the axis at the first increment, top out at the second, through the axis, top out. So there's one little cosine curve. Maybe we'll just do one more over here. So it goes going left to the first increment through the x-axis, tops out at 3. Second or third increment, let's see, first, second, third increment goes through the x-axis and then tops out again. So we won't get quite as many vertical asymptotes on this one. We'll see what we got here. So I draw in a vertical asymptote there, 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 there. And because I accounted for the negative when I graphed negative 3 cosine of x, I will have it. It will be flipped, reflected from it. So it's all taken care of here. So right here I have a dot here. And there's one cycle. And this other half here, there's another cycle. So there's 2 cycles of the secant. So those are the other 4 graphs.